The densest stars you'll never touch, city-sized, sun-mass monsters bend light, crack their own crust and flicker like cosmic lighthouses. Tonight, neutron stars are weirder than we ever imagined. Start at their birth, a massive star's core collapses in a supernova. Gravity crushes protons and electrons into neutrons. What's left is a compact remnant, about 1 to 2 solar masses packed into a sphere roughly 20 kilometers wide. Imagine a sun's worth of mass squeezed into a city. A teaspoon of this stuff would weigh like a mountain on Earth. It's matter at nuclear densities, nuclei elbow to elbow, physics pushed to its limits. Gravity at the surface, hundreds of billions of g. Time dilates, light bends, escape speed a good fraction of light, yet it's not a black hole. Photons still climb out, warped and delayed. Some neutron stars beam radio and X-rays from magnetic poles. As they spin, we see lighthouse flashes, pulsars, nature's precision clocks. The fastest? About 716 times per second. Then they glitch, tiny sudden spin-ups. It's like a cosmic clock skipping ahead a tick, revealing strange superfluid physics inside. Others crank the magnetism to absurd. Magnetars wield fields up to 10 to the 10, or even 10 to the 11. Tesla. That's enough to twist their crust and spark giant flares across the galaxy. Picture field lines snapping, the crust cracking in a starquake and a burst of X-rays and gamma rays screaming outward. Brief, blinding, bonkers, zoom into the crust. Mountains, centimeters tall, yet they weigh like Everest because gravity pins everything down with brutal force. Beneath that, matter self-organizes into nuclear pasta, gnocchi, spaghetti, lasagna phases. Wild shapes formed by nuclear forces and extreme pressure. It's the strongest material you'll never touch, exotic lattices that may anchor those tiny mountains and affect how the star rings. Deeper still, superfluid neutrons, superconducting protons and quantized magnetic flux tubes. Quantum mechanics scales up and runs the show. Those superfluids rotate by forming vortex lines, pin them to the crust, unpin them all at once, and the star's spin jumps. That's a glitch. Even the light we see is distorted. Gravity bends photon paths so strongly you can glimpse more than half the surface at once. Their thin atmospheres, ionized plasma, can polarize X-rays and imprint spectral fingerprints. We read those clues to probe the surface. Freshly born, they're blazing hot, millions of degrees, but they cool fast by shedding neutrinos, those shy particles that slip through almost everything. Over thousands to millions of years, they fade from white-hot to merely warm by astronomical standards. Still exotic, still extreme. Put a neutron star in a binary, and things get dramatic. Steal gas from a neighbor and you build an accretion disk that blazes in X-rays. Sometimes that stolen fuel ignites in a thermonuclear flash. Type 1 X-ray bursts. Brief, bright, and periodic. Accretion also spins them up. Over time, they become millisecond pulsars, whirling buzzers that rival atomic clocks, and when two neutron stars orbit together, they chirp out gravitational waves as they spiral inward. Energy radiated as ripples in space-time. Merge them and you get a kilonova, heavy elements forged in the ejecta, gold, platinum, lighting up space with a fading, colorful glow. In 2017, Jibabanan 70879 let us watch and listen. Gravitational waves plus a kilonova's light. Proof that neutron star smash-ups seed the cosmos with precious metals. That is wild alchemy, space-time ripples, our process chemistry, and a fireworks show you can see across a galaxy. How do we measure something so extreme? Pulsar timing maps their spin to microseconds, spectra and polarimetry probe fields and atmospheres. X-ray light curves reveal hotspots sweeping across warped horizons. Their shapes encode mass, radius, and spin. Enter NICER on the space station. It watches pulsars and X-rays to constrain the neutron star equation of state, how squishy or stiff ultra-dense matter is. Combine timing, spectra, and waveforms, and you get bands of possible radii for given masses, closing in on the true nature of neutron-rich matter. It's a tug-of-war between quantum pressure, nuclear forces, and gravity, a three-way showdown in a 20-kilometer arena. Meanwhile, pulsar timing arrays listen for the faint background of gravitational waves by tracking dozens of millisecond clocks across the sky. Precision, patience, and a lot of clever math turn flickers of X-rays and radio waves into interior blueprints. No lab on Earth can make a neutron star, but the universe kindly supplies them, and we read their light like lab notes. Big picture. These remnants connect supernovas, quantum fluids, nuclear matter, magnetic fury, and gravitational waves. One object, many frontiers. Between those bursts of brilliance, most of space stays quiet and dark. Neutron stars are tiny islands of extreme. They aren't weird because stars aren't normal. They're weird because physics under pressure does things our intuition can't. One more nuance: surface temperature and radiation danger aren't the same. A cool magnetar can still fry you with high-energy photons and particles. That's why we study both. Thermal emission to take a temperature and high-energy emissions to gauge the hazards. Balance the models with the measurements, and the picture sharpens. Beams, quakes, pasta, waves. All one story. Put it together. A core collapse birth, a crust of exotic matter, a superfluid heart, magnetism off the charts, and clocks precise enough to test relativity. They are laboratories in the sky, tiny, terrifying, and perfect, where quantum mechanics, nuclear physics, and gravity meet. Manage the beams, count the ticks, model the glow, and the weirdness becomes a window into fundamental physics. Most wander the galaxy quietly. A few blaze as pulsars, the rarest thunder as magnetars. All of them rewrite our expectations. From single atoms to warped spacetime, these stars knit together the scales of the universe. Not just dead cores, but cosmic laboratories, compressing physics into a 20-kilometer riddle. So next time you hear a pulsar's tick or see a kilonova's bloom, remember, we're watching extreme physics perform live, and every measurement brings that strange interior into sharper focus. Recap. Supernova births, city-sized mass, furious gravity, pulsars and glitches, magnetars and starquakes, nuclear pasta and superfluids, accretion bursts and mergers, nicer pinning down the equation of state. Neutron stars prove that the universe hides its strangest ideas in the smallest, darkest places. Keep wondering, keep looking up, stay curious.